For the first problem, if we take a section through the right hand panel, then we will achieve something like this. Now, one thing quickly you have to find out is the direction of the reaction force on the right hand support. Now let's say given the direction of the load, the reaction force would be upward. Now it's fairly easy to find out what would be the directions of the member force in AD. To resist this vertical reaction force, the member force in AD must be in this direction, or in other words, in tension, because the other two forces will not contribute towards the vertical reaction force. So in this problem, A is the correct answer. For this particular problem, one thing to note here is that you have got a force acting at point C, horizontal force, plus you'd expect a reaction force from this roller. So although number 1 and number 4 are quite close in these two respects, but in 4 you have got these extra forces at joint A, so that is not correct. So the correct answer must be this number 1. For problem number 3, we will take a section through the first panel, and that would look something like this. Now if we draw the internal forces in, then the member forces in AB must be acting in the tensile directions to resist the vertical component of the force, because the other two members would be only horizontal, either left to right or right to left, we don't know, but this must be in tension. This particular problem is fairly simple. If you isolate joint B, for example, then we will be able to find out the forces in that member AB. So the member force would be, so vertical equilibrium would dictate that member AB will have 0 force in them. So this is the correct answer. Two things to note in this case. First of all, for the free body diagram of the left hand side of the cart, whether the support reaction force are truly represented. Now the support at G is a pin, so it should have a vertical force, reaction force, and a horizontal reaction force. Both are possible. Now whether they will have or not depends on the load that has been applied. So if we apply that criteria, then you'll see this is one candidate and this is another candidate. Okay. Now if you look at closely now all the other force that has been applied, so between these two forces that I rightly applied, where you have got all the forces are shown tensile, so that's okay, but the force at C is wrongly put in this case. So this is not the right diagram, this is indeed the correct free body diagram. The main question involved in this problem is to determine whether the forces in this cable is under tension or compression, because under compression cable would not resist any force, so that would become, the whole truss would become unstable. So as an exercise, we have to find out what is the force in this, nature of the force in this cable, either it is tensile or compressive. So if we take a free body diagram by taking a section taking a section through the middle point. Then we get this as a free body. Now what about the forces? Now to resist the vertical forces, the force in cable must have to be under tension, and then of course there would be other two forces that would be acting on the vertical. But main point is that force in the cable is under tension, so the truss is stable. In this problem, what you have to consider is the direction and the nature of these two forces in terms of the reaction force these two forces would generate on the two supports. So you have got the forces, horizontal one, I'm doing it by green line here, and a vertical one by this line there. Now what would be the direction of the forces due to these two? Now for the vertical forces that has been applied, you would expect that two reaction forces would be on two supports would be the vertical direction. But for the horizontal forces, if you consider the reaction force direction, this side it would be upward, but that side it would be downward. Why it is downward? Because if you take moment of these horizontal forces about this support point, then the force on the reaction force on the left hand support must go vertically downward to compensate the moment due to the horizontal force. So this is essentially the problem, is that if we don't know the relative amount of these two forces that has been applied, these horizontal and the vertical forces, we don't know exactly what is the value of net forces in the left hand side. Is it going upward or? So if R1 is greater than R2, then reaction force would be vertical, and if it is other way around, reaction force would be downward. So as we don't know this, then it's nearly impossible to find all the member forces. For this particular problem, what we have to do is find out the reaction forces at A and B. So the reaction forces at A, let's say it is a roller, goes from left to right, and at B it's a pin, one force goes from left to right and another force goes upward direction, let's say. Let's name them R1, R2 and R3. Now by considering equilibrium of the whole structure, R2 must be equal to F, and R2 will act in the upward direction as shown. To calculate the force in member AB, we need to isolate joint B with the reaction forces shown as in there. So as we have made a cut, so there would be a force in member BC and there would be force in member BA. Now by considering the equilibrium of these two isolated joint B, we could clearly say that FBA must be equal to R2, so which is F, and we could say that's with a positive sign because my choice of the direction is correct, because R2 is going upward, so FBA must be acting downward. Now from this point we could say that the correct answer would be plus F, so whatever value of F that you have been given. For the final problem, we would start by looking at the reaction forces at two supports A and E. So we'll have a vertical reaction force at E. We don't know the direction yet, but we have shown it going vertically upward. We'll have a vertical reaction force as well as a horizontal reaction force at A. So let's call those forces as R1, R2 and R3. Now if you take moment about point A, because I'm interested in R3 to start with, so if we take moment about point A is equal to 0, then R3 would try to rotate the truss in the anti-clockwise direction. So what is the moment? Moment is R3 times 6, and it is in the anti-clockwise direction. It will try to rotate the truss, so I will use a negative sign. What about F? F about point A is going to rotate the truss in the clockwise direction. And what is the lever arm for force F? That's multiplied by 4, and that's with a plus sign because it's acting clockwise. That must be equal to 0. So this gives us R3 is equal to 4 over 6F. So if I simplify that, that would be 2/3 F. So 2/3 F is the value of R3. Other thing to note, that this force is acting vertically upward. So my choice of R3 is correct. We probably wouldn't do that member AE right now. So for that we could try to do that. So let's take section at joint E. So if I take a section at joint E, what are the forces that we have got? So we have got an R3 force there, which is the same as 2/3 F. And then I have exposed three members. I have exposed this member, and that member. Now as before, we will say all of are tensile to start with. So this force is forces E to D. This force is force E to C, and this force is what we have to find out is force E to A. That's what we have to find out. Now we could possibly get an idea of what a force E to D would be if I take an equilibrium of joint D. So if I take an equilibrium of joint D in here, then I could say, okay, this force is in this case F D to E would be equal to 0, because vertical equilibrium of joint D would mean F to D equal to 0. So that means F to ED is also 0. So this force is 0. Okay. So if that force is 0 and 2/3 F is acting in the upward direction, so vertical equilibrium should be maintained if FEC is compressive. So the direction of FEC would be in the compressive direction. So that would then the vertical component of it would balance the 2/3 F as the reaction force. What would be the value of FEC? To do that, we probably need this angle. Let's say this angle is theta, for example. So this is same as theta there. So we can find tan theta is equal to 3 over 4. That gives you theta is about 36.9 degree. So if you do that, then you need to find out here that FEC's vertical component, which would be cosine theta, is 2/3 F. Okay. So putting back theta is equal to 36.9 degree, we can find the value of FEC. So cosine of 36.9 degree would be 0.8, so that is 2/3 F. So this will give me FEC in terms of 2/3 F as 0.833 F. Now it's now easy to find out what would be FEA. So FEA would be nothing but FEC sine theta. And what is theta? Theta is 36.9 degree and FEC is 0.833. So if you do the calculations all right, then you will get FEA is equal to F over 2, and that is in the tension directions. So whatever value of F that you have been given, the force in member EA would be half of that and in the tensile direction.